Okay, in this video we're going to take a quick look at the standard reduction potential table and discuss how you would read it and how you would use it to figure out whether a reaction would be spontaneous or not. The first feature of this we've got to look at is the sort of fact that it's a standard reduction potential table, and therefore the higher you are on this table, the more likely you are to be reduced, to take electrons and add them in to gain electrons. So as you go up on this chart, what you're looking at is a higher likelihood of being reduced okay, so we have a higher likelihood of being reduced as we are moving up the table. That also means that therefore the things at the top of the table are better oxidizing agents, okay, because they're much better off at gaining electrons and therefore taking electrons away from other things and oxidizing them. Alright, what that means is if you look down at the bottom of the table, higher likelihood of being, in this case, it's going to be oxidized. Right, because if you're more likely to be reduced on the top, the ones at the bottom are more likely to be oxidized. Alright, so given that we understand that, let's take a quick look at the sort of left to right side of this thing. So if you split down these reactions, you notice that the left side has the electrons. These are all written as reductions, and therefore the left side is the oxidized form of these chemicals. And then on the right side, it is in its reduced form. Okay, this becomes important when we go and think about whether a reaction is going to occur or not. So if we look at the top one there, fluorine, right? F2 gas has an oxidation number of 0. If we were to do it out, Ag+. Okay, so we had a silver ion, and we also had present lead, solid lead. Okay, if we look at the two of these, the one that wants to be reduced, again looking at our sort of writing over here, higher likelihood of being reduced, is going to be the one that's higher up on the table. That's the Ag+, going to Ag, that reduction. The lower down one, lead 2+ going to lead, does not want to be reduced as much as silver does, and therefore it is more likely to be oxidized while the silver is reduced. So if we look at two important factors here, silver, Ag+, is higher, and because it's higher on the table, it wants to be reduced. It is in its oxidized form currently, so it can be reduced and go to form Ag solid. The lead, meanwhile, which is lower down, is currently in its reduced form. Okay, but since it doesn't want to be reduced as strongly as the silver is going to take those electrons, and the lead is actually going to give up electrons and become oxidized. Okay, so the lower down on the table of a reaction will be oxidized, the higher up on the table will be reduced. So in this case, where we have something up and to the left, silver ion, and something down and to the right, solid lead, okay, we have a spontaneous reaction. The Ag+ will be reduced to Ag solid, the lead solid will be oxidized to lead 2+ ion. Okay, so now let's go ahead and wipe that clean and take a look at a different scenario. Okay, let's say we had the opposite. So we had silver, but this time we had silver solid metal, and we mixed that with lead 2+. Okay, so we had the lead 2+ ion. Well, here you can see that no reaction is really going to happen, okay? Because as we said before, silver, which is higher up, has a higher likelihood, higher desire to be reduced, tendency to be reduced, however you want to think about that. And what that means is that silver wants to take the electrons, but notice it's already on the reduced side. It's already over on the right, and therefore the silver is already reduced. It may want to have electrons, but it already has them, so it's done. It can't really react. The lead, meanwhile, which is lower down, it would want to be oxidized relative to the silver, and it is, right? We're currently over here on the left side. And so what that means is we can't have a spontaneous reaction occurring between these two, because as we showed before, the spontaneous reaction has the silver becoming Ag solid and the lead becoming Pb2+, and that's what we have here. So essentially we're looking at the reverse reaction of what we just showed, which was spontaneous, which means this is the non-spontaneous reaction, right? Anytime you have a spontaneous reaction and you flip it, you're then looking at the non-spontaneous. So things that are up and to the right and down to the left won't react because the up and to the right species is already reduced and it wants to be reduced, so we're done. Okay, so that is going to be how you can use this table and think about this table. I think one more key way that you could think about this is to look at something and list things in terms of being a better oxidizing or better reducing agent. So we'll do one of those. Okay, so if these four, cobalt, cobalt 2+, cadmium, and cadmium 2+, we're going to try and figure out which of the ones will be the better reducing agent. And then which would be the better oxidizing agent. So the first thing is to find these reactions on the table, and if you take a look, sort of cobalt is right here, cadmium is right here, so they're right next to each other. Now if we want to find the better reducing agent, then we need to find the thing that is most likely to be oxidized. Okay, so taking a look at our reaction here, the most likely to be oxidized, higher likelihood of being oxidized as you go down the table. So it's going to be either the cadmium 2+ or the cadmium. Okay, and now we need to figure out which side it's going to be. Well, if you're on the left, you're already oxidized. Not really going to help you out as a reducing agent because you can't really react to become oxidized. You're already there. Therefore, it's going to have to be down and to the right, so it's going to be this cadmium right here. So solid cadmium, lowest and to the right, is our best reducing agent of that list above. Okay, it's the most likely to be oxidized to go and form cadmium 2+, and therefore give up its electrons to something else. The best oxidizing agent, therefore, is going to be something that's most likely to be reduced. Well, higher likelihood of being reduced as you move your way up the table. So the cadmium reaction is now out, and we're looking at the cobalt. And in order to be reduced, you have to also be on the oxidized side, heading on the left side, heading towards the reduction. So cobalt 2+ right here would be the best oxidizing agent of those four. Okay, because it's the highest up, most likely to be reduced, and it's on the left in oxidized form, and therefore it can accept electrons and become reduced. Alright, so that's sort of the quick bit of the table, and then in the next video what I'll do is I will quickly break down a reaction that will occur and show you how to find the delta G given the E of cell that you can calculate from this.